Good afternoon, dear students. Let us continue the class, the section 2 of the electrochemistry 2. That is, we are to discuss the mechanism of the single electrode and the single electrode potential here. A single electrode consists of a metal rod or strip in contact with its salt solution. It generally constitutes a single electrode. So when a metal is in contact with salt solution, there is a surface of separation between the metal and the solution. Okay, there is a surface of separation that is usually called intersurface. Because of the tendency of the metal to lose or gain electron with respect to the metal ion, that develops an electrical double layer due to the accumulation of positive and negative charge at the vicinity or the intersurface of the metal and the salt solution. Okay, there is an accumulation of opposite charges at the intersurface. And therefore, the intersurface acting as an electrical double layer where there is a potential develops. And that potential is usually referred to as the single electrode potential. That means the potential that develops at the intersurface at equilibrium is called the single electrode potential, represented as EM n plus aqua bar M. Okay, double single line M, or E M plus vertical line M. Okay, where M plus vertical line M stands for the metal ion, and single vertical line stands for the interface or intersurface between the metal and metal ion. Okay, if this metal and the metal ion is in their standard state, okay, then the representation of the single electrode potential become E0. Okay, E0 M plus bar M. What is the standard state actually? That is a standard solution. Okay, sorry, standard state is a state of the electrode in which the aqueous solution is, or salt solution is of 1 molar concentration. The salt solution is of 1 molar concentration which is kept at a temperature of 25 degrees Celsius. It is kept at a temperature of 25 degrees Celsius and a pressure of 1 atmosphere. So any aqueous solution, okay, or any salt solution in which the metal is in contact is of 1 molar concentration at a temperature 25 degrees Celsius and 1 atmosphere pressure is called standard state. Then the EMF developed is called, the single electrode potential developed is called E0. Okay. Then the mathematical or scientific definition of the single electrode potential is that it is the equilibrium potential that develops at the surface of separation of metal in contact with its salt solution due to the accumulation of opposite charges resulting from the tendency of the electrode to lose or gain electron. The single electrode potential is given by Nernst equation. For the electrode reaction, Mn plus aqua plus N electron, Ne minus reversibly give M solids. Okay, that is, customarily the electrode reaction should be represented in terms of reduction. All electrode reaction should be represented in terms of reduction according to IUPAC custom. then any half electrode reaction is represented like this. That is in the form of reduction. Mn plus aqua plus N E minus reversibly give M solid. Therefore, the single electrode potential E Mn plus aqua M is equal to E0 Mn plus aqua M, that is the standard single electrode potential, minus 2.303 RT by NF log M solid divided by Mn plus aqua. Here, the concentration of any material in the solid state is taken as 1 or unity, that is the universal constant. That is, activity is equal to 1, that means concentration is equal to 1. Therefore, the equation can be rewritten as E Mn plus aqua M, okay, E Mn plus aqua vertical line M, that is the single electrode potential, is equal to E0 Mn plus aqua bar M, that is standard single electrode potential, plus, okay, sign changes, plus 2.303 RT by NF log Mn plus aqua, where Mn plus aqua represents the concentration of the salt solution. Again, you remember this equation, I repeat. E single electrode potential is equal to E0 single electrode potential plus 2.303 RT by NF log Mn plus aqua, provided the single electrode reaction is written in the form of reduction. Therefore, the E cell is equal to E cell, that means the EMF of the cell E cell is equal to E cathode minus E anode. Okay, E cathode minus E anode. If it is in the standard state, it is written as E0 cell is equal to E0 cathode minus E0 anode, that is equal to E0 right minus E0 left, or is equal to E right minus E left generally. Let us consider the standard and reference single electrode. There are different types of single electrode depending on its assembly or technical assembly. I wish to mention only very few. So there are different types of single electrode depending on the assembly. Okay, that is metal ion single electrode, gas electrode, and metal insoluble salt, soluble salt containing anion of the salt like column electrode. But I wish to explain very few single electrode. They are standard and reference single electrode. One is standard hydrogen electrode. This is a gas electrode. Standard hydrogen electrode is a typical gas electrode. Okay. It consists of standard hydrogen electrode, otherwise called a normal hydrogen electrode, consists of a platinum electrode in contact with 1 molar HCl solution. Okay, 1 molar HCl solution. The pure dry hydrogen gas is passed through it at a pressure of 1 atmosphere and 25 degrees Celsius. The potential of the electrode is arbitrarily taken as 0. That is very important. Okay. So, an hydrogen electrode becomes a standard hydrogen electrode as He if the hydrochloric acid concentration is 1 molar and the hydrogen gas is at a pressure of 1 atmosphere and at a temperature 25 degrees Celsius, and its potential is always arbitrarily taken as 0. Hence, it is called a primary standard electrode used for measuring all other single electrode potential. And the single half electrode reaction involved in an hydrogen electrode is, that is, half H plus aqua plus electron reversibly gives half H2. Remember, always the electrode reaction is the present in terms of reduction. So the electrode reaction, the reversible, or it is an electrode reversible with respect to H plus ion. Hydrogen gas electrode is an single electrode which is reversible with respect to H plus ion. And for SHE, that is standard hydrogen electrode, the H plus ion is of 1 molar concentration and its Z0 is 0. So it is the only one primary standard electrode used for measuring other single electrode potential. Okay. Then, sign of single electrode potential. That's very important, and please students, you should avoid the confusion in the sign of the single electrode potential. Nowadays, single electrode potential are always expressed in terms of reduction potential. Okay. Even though the metal is undergoing oxidation, when it is in contact with the salt solution, it should be customary that the single electrode potential are always expressed in terms of reduction potential. That is according to IUPAC. There is no concept of oxidation potential. So all our single electrode potential, that is, we are expressing, are in terms of reduction potential. The sign of the single electrode potential, that is the reduction potential, are either negative or zero. Positive, that is either negative or positive, depending on whether it undergo oxidation or reduction respectively when combines with SHE. Okay, that means the single electrode potential is negative if the metal undergo oxidation when coupled with the SHE, and it is positive, the single electrode potential is positive when the metal undergo reduction when coupled with the SHE. So we look into which metal undergoing oxidation and which metal undergoing reduction. Okay. Generally, all the metal ion which has a greater tendency to undergo oxidation than hydrogen, such metals have the oxidation is spontaneous and reduction is not spontaneous. So such metal ions electrode, single electrode, the reduction potential, that is the single electrode potential in terms of reduction potential, is negative, because here oxidation is spontaneous and the reduction is not spontaneous. Hence, it is written in terms of reduction potential, that is become negative. Example, okay, all the metal that lie above the hydrogen means that are more oxidizable than hydrogen or more electropositive than hydrogen are said to possess the single electrode potential negative sign or reduction potential negative sign. Example are Na plus Na, K plus K, Mg2 plus Mg, Zn2 plus Zn. There are various other examples, that is lead 2 plus bar lead, then in nickel 2 plus bar nickel, etc. But those bar metal ion which are less electropositive than hydrogen and are less oxidizable than hydrogen, and in such cases the reduction is spontaneous. The reduction becomes spontaneous. Okay. Such metal ion single electrode type, the reduction potential become positive. You think those metal ion which are less oxidizable than hydrogen, in which the reduction is spontaneous. Okay, such metal ion assembly, the single electrode potential or the reduction potential is positive. All the metal ion that lie below the hydrogen, okay, that below the hydrogen, which are less electropositive than hydrogen, have the positive reduction potential. Example, copper 2 plus copper, Ag plus Ag, Au 3 plus Au, etc. And again you have to remember the position of the hydrogen is exactly in the middle with a zero reduction potential, that is plus or minus 0. Okay, and all the metal ion above the hydrogen have negative value of reduction potential, and below that they have the positive value of the reduction potential.